Okay. So, previous class we were discussing about cleavage reactions, particularly alpha cleavage reactions, and we took saturated acyclic ketones and we tried to understand how it undergoes cleavage reactions. In this class, what we will do is that, as I mentioned, we will take a saturated cyclic systems and try to understand how the chemistry works. Okay. So, in saturated cyclic systems, we said that we are going to discuss 6 membered rings, then 5 membered, 4 membered, and if we have some other examples of higher member ring cycles, we will see that. Okay. So, we will start with the 6 membered ring system. So, so basically the 6 membered ring we will consider cyclohexanone. Okay. So, you guys know once I shine light, what happens? It undergoes, gets excited to its singlet state, and as like a cyclic systems also undergoes intersystem crossing. To give me my triplet. After this, you know that it undergoes alpha cleavage reaction, right. So, we get an alpha cleavage to give me a acyl and alkyl radical, which is inbuilt. Since it is a cyclic system, you get both. On one end you will get an acyl radical, another end you get an alkyl radical. So, this is your primary process. Fine. Now, what we will do is that we will consider the secondary process and see what happens to these radicals. Okay. So, I got my acyl radical. So, what it can do now? So, you have studied one, it can undergo a decarbonylation, right. I get my decarbonylation to give me what? What is this? 1, 2, 3, 4, 5. So, you get a 1,5 diradical. Fine. What 1,5 diradical can do? What are the reactions 1,5 diradicals can do? They can do a recombination, right. To give me cyclopentene, or other thing what it can do. You have studied about 1,5 diradicals, right. So, 1,5 diradicals can recombine to give me a cyclopentene, or it can abstract an hydrogen. Okay. So, you have an hydrogen abstraction process, intramolecular hydrogen abstraction can take place to give me my alkene type derivatives. So, next we will see what is the other process we have studied in the secondary. One, we have studied alpha cleavage reaction, another we have studied this that is what decarbonylation, to it undergoes a decarbonylation to give me a 1,5 diradical, and then we studied that 1,5 diradical can recombine or it can abstract an hydrogen to give me an alkene. That is what we studied, right. So, I got product 1 and product 2. So, what other things we studied in the secondary process? Yeah. So, we studied a process called intramolecular hydrogen abstraction. In this case, it will be intramolecular hydrogen abstraction. I can think of two ways. One, your acyl radical can abstract an hydrogen, okay, to give me an aldehyde, unsaturated aldehyde. You can get this, or my alkyl radical can abstract an hydrogen to give me ketene. And this it does one more reaction which is very important, this acyl and alkyl radical, this system. Any idea what it can do? One, it does decarbonylation, which you have studied. Another is intramolecular hydrogen abstraction, where acyl radical can take an hydrogen or your alkyl radical can take an hydrogen. So, you get two products. Then beta, it undergoes very good radical recombination in this stage itself to give back my starting material. See, this is very important reaction, this radical recombination. You will understand basically why. Next example, I will let you know how this radical recombination plays an important role. Okay, in this reaction, you say that yes, sir, I am getting back my starting material. But if you take some other molecules, I will show in the second example how this radical recombination is important. Right? So, what happens? You take a cyclohexanone system, when I shine light, I get a decarbonylation product that is coming out of 1,5 diradical. See, the more important is that you have to study diradical systems. So, you get 1,5 diradical, get the system, plus you get your the same, yeah, since it is same you are not writing it, but anyhow you should know that these two products you get out by your decarbonylation, that is from the 1,5 diradical. This is your intramolecular hydrogen abstraction, and this is from radical recombination. So, I can get like 5 products, fine. Now, what we will do, we will take another second example where I am taking a cyclohexanone. Now, we will take this type of cyclohexanone system, okay. And now we will see whether we can apply the same knowledge, okay, of the from the first example. Like we have studied like decarbonylation, we have studied intramolecular hydrogen abstraction, radical recombination. Can we apply the same knowledge here? So, yes, your first step is always, you know, once you shine light in cyclohexanone system, it is singlet, then it undergoes intersystem crossing, it is triplet, then you can do your alpha cleavage. Since it is a symmetrical, you does not worry about much whether this side or this side. So, you end up with an you get this. Up to this it is fine, it is like a primary process which you know, okay. Now, we will see what happens to this radical, how it does the secondary reactions, okay. So, I have my system like methyl, okay, you have this radical. Now, what it can do? What this can do once you get this radical? In previous case you saw decarbonylation, intramolecular hydrogen abstraction all taking place. In this case, yeah, it also happens, but another important thing happens here. What you can see?
You can get the other stereotype.
Yeah, you can always have this bond rotation, right? That is your C2 to C3 bond rotation can happen. Right. So, you will get then get now this system, right. Now, what happens? Your both are like same type of radicals, right. So, if this is undergoing 1,5 if this undergoes decarbonylation to give me 1,5 radical, then this also should undergo same decarbonylation to give me 1,5. If this is going to do my intramolecular hydrogen abstraction, then I have to do for this also. So, you see that. Now, what happened once I put 2 methyls, the formation of product will be more. Okay. So, what we will do first, we write for this. What it does a decarbonylation to give me so this is not there. Okay. So, you get your 1,5 diradical. You know that what 1,5 diradical can do. 1,5 diradical can undergo a radical recombination fast. To give me a methyl. Right. Then you know that it picks hydrogen, but that is you get a minor product. We do not worry right now on that. You can write that product also. Then you get your intramolecular hydrogen abstraction. You can think about this intramolecular hydrogen abstraction. So, what you get? You get your, if I pick an hydrogen from here, you get your aldehyde, right? Shall we write that aldehyde? So, methyl here. So, what happened now? I am generating a double bond there, all right. If I generate a double bond here, so what it means? I am now fix my methyl, whether it is cis, trans, EZ, we have to do that. So, since it is outside, fix it as methyl here. Okay. See, these are very simple thing, but you have to find it out. Okay. If I do the same chemistry from this radical, for example, I am doing the same intramolecular hydrogen abstraction, then what product I should get? See, my methyl will be inside, right. So, I get now like 2 different alkene products. If I do my radical, that is decarbonylation, the radical, and this recombines just due to your C2 C3 bond rotation. See, I am getting like different products now. I get like this one of the product, you can get this, right. Then one important reaction happens, that is what I said, this can undergoes a radical recombination, then I should get a cyclohexanone, which will be different from your product. See, mostly you are going to end up like, see, I am not, no one gives you directly cyclohexanone and asks you. You will get system like this. Then you have to understand, like, once I fertilize, and you have to write all the products at the end of the day. It's not like writing only one product. Okay, you should know to write all the products. So in this case, I have 1, 2, 3, 4, 5. If I miss this C2 to C3 bond rotation, I am going to end up with only 2 products, right. But these others are also important, and all these products are isolated and characterized. Okay. So we have several examples like this. I am just going to give you this, and then we will, in the assignment I will give you several examples based on this type of mechanisms, right. Okay. So now we will take very simple cyclohexanone system, okay, and try to understand this product studies, like if you do it in vapor phase or if you do it in liquid phase, which products will be predominant. Okay. So first, for that we have to write the products. So you just can you write all the products for this? So here you know that you have an option of this bond A or B. Okay, you know which to cleave. Okay, which one is A or B? B, because you are going to get a secondary type of radical. So I can get this product. So if I want to write the products of this, so always try to write your radicals. Okay, that will give you information. So it can undergo a decarbonylation. So it is a 1,5 diradical. And basically you should get 2 products from here. One product like this, get one like this. Because this can abstract an hydrogen from here, giving me an alkene, and this type of alkenes are stable rather than forming an alkene this side, right. Substitute the alkenes. Other thing you can think about is your intramolecular hydrogen abstraction. You get okay an aldehyde. See, this will be the major product, but you can get another stuff. right, you can get this product also, that should be a minor. So, you get a major product. Okay, now, if I do this reaction in vapor phase, like without any liquid or any solution, just take my cyclohexanone, methyl cyclohexanone, and just carry out this reaction in vapor phase, which product will be dominating? Which product you think will dominate? Yeah, your decarbonylation, right? Decarbonylation will happen in vapor phase. This product will be more dominating, but once you do the reaction in solution, then your intramolecular hydrogen abstraction process takes place faster. Okay. So, see, in vapor phase your system does not have much, okay, to be stable. So, what happens, another alpha cleavage to the carbonyl happens, and the radicals just gets off the carbon monoxide, giving you the 1,5 diradical. But in liquid phase it has much interaction with solvents and other systems. So, it stays and it sees some hydrogen abstraction is possible. Okay. That is why it happens. If you do same system in zeolites and everything, you can see different chemistry happening. Okay. But more on the vapor phase, you try to get more decarbonylation product. Norris type 1 reactions most of the time is encountered in vapor phase. Okay. So, this is some examples on 6-member ring system. Okay. Now, we will take some examples on 5-member ring system. Okay. What 5-member rings can do? See, in each case you will get different radicals. In 6-membered you got 1,5 diradical system, and 5-membered you will get 1,4 diradical system, and each diradical has its own chemistry. Okay. They undergo a radical recombination, and then 1,5 it undergoes a radical recombination, same way it abstracts an hydrogen, but it is not necessarily true to be 1,4 diradical. 1,4 diradical chemistry is entirely different. So, we will see how it works there. Okay. So, the primary photochemical process most of the time are same, except for some cyclic system. For example, cyclic butanone, it never undergoes any intersystem crossing. Okay. Otherwise, most of your primary process which happens in the light, okay, excitation to singlet, n pi star, then intersystem crossing, and then alpha cleavage will be most of the time same. The secondary process will vary, okay, depends upon your radicals and what system you are doing the chemistry, everything. So, now we will take 5-member ring systems. So, that is why initial class itself I said, if you are strong in spectroscopy and free radical chemistry, you can do most of your photochemistry. Okay. So, we will take the simplest cyclopentanone system. Okay. The chemistry is same like that, like initially the for cyclohexanone and cyclopentanone, the primary photochemical process will be same. So, S1, okay, then you get intersystem crossing, okay. get a system like this, which is more or less same to your cyclohexanone. Now, we will see how this acyl and alkyl radicals of cyclopentanone behaves. So, we will see the secondary process now, how they are different from the initial one. So, you know it undergoes decarbonylation. So, what radical here you are getting? 1, 2, 3. We are talking about 1,4 diradical now. Okay, what does 1,4 diradical does? 1,4 diradical does hydrogen abstraction. First thing, 1,4 diradical tries to do your recombination to give you systems like this. Recombination is allowed. You call it recombination or you call it a cycloaddition or the another important thing of 1,4 diradical system is your cleavage, okay, your beta cleavage. That happens very fast in 1,4 diradical, that you cannot see in 1,5 diradical systems. 1,5 diradical system undergoes intramolecular hydrogen abstractions. 1,4 does not do that most of the time, it undergoes cleavage. So, if it undergoes cleavage, you get an basically you should get 2 molecule of ethyl. Okay. So, you should get this type of system, right, 1,5 diradicals. This type of system undergoes a recombination to give you cyclopentanone. Yeah, it always happens this to give me back my, but this is the major product. Okay, the chemistry in cyclopentanone system. Okay, once you make your ring strain, keep on straining your ring, decarbonylation process keeps on dominating. Okay, so that's why like cyclohexanone. Once you take cyclohexanone, immediately you can think about formation of 1,4 diradical pentanone system. But anyhow, you can see minor products of your recombinations, plus you can see your intramolecular see about your intramolecular hydrogen abstraction, that is you can think about getting your ketene, right. You can get your ketene, or at the same time you can get your aldehyde. So, I have taken a simple cyclopentanone system. So, you can think about so much of products. Okay. So, remember about the diradical formation, that is more important. See, once the ring becomes strained, or I am giving you an example where the rings become strained, then you should understand whether this reaction goes whether decarbonylation will be the major product, or it is recombination, or it should be an intramolecular hydrogen abstraction, that will be little bit tricky when you go for a higher type of examples, okay, which will deal. So, I am taking a cyclopentanone system where you are trying to make sometime like stain type of rings into the. Okay, now, when we fertilize this, you get S1, then inter-system crossing, you get T1, that you know for sure. Then it undergoes an alpha cleavage, give me a product, can do an alpha cleavage here because it is more like same molecule. So, I get a radical of this type. Now, what happens in the second? Up to this it is primary process, which you know, it is good, but what happens if you go for the secondary process now? Now, what you can expect from this happening? Cyclopropane will involve that is the one, because you are getting, you can have think about many reactions, right. One, it can undergo a decarbonylation, okay, to give me my 1,4-diradical system, or it can undergo an intramolecular hydrogen abstraction from acyl or alkyl, or it can do a radical recombination. So, you have like 3 possibility when you think about, like that you write always. So, in this now you have to eliminate, because it is become a very specific examples. So, whether intramolecular hydrogen abstraction happens here, can it happen? See, if I pick an hydrogen from here, I am going to create an alkene, which is like really, and generating a ketene in this type of systems again hard. So, intramolecular hydrogen abstraction I can eliminate out. Then I will go for radical recombination, like you are again trying to make a highly stained ring. So, it is not going to do that. So, that is over. So, I have left with only one secondary process, that is your decarbonylation. So, it can then you can have a system like this. So, you get a radical system, right. Now, again it becomes now 1,4-diradical system. We have studied very clearly that 1,4-diradical system. That is why I said now 1,4-diradical system. Again 1,4-diradical system, you have two options. Okay. One option you are is cyclization to give me a cyclic product. So, you think like whether I can cycle this, it is very hard because I am trying to. So, I am eliminating that process. Then 1,4-diradical system, what it does? It does a beta cleavage. So, right. So, that is how now you have to see, when you go for an higher examples, now you have to decide which are the secondary process will be dominating. You cannot keep on, see, if I give a simple molecule and ask you to write all the products, yes, you can keep on writing once you know these are the process. But once I give a specific molecule and ask you to write the major product, the given system, then you have to give me the major product. That time you have to understand which is the secondary process will be like dominating in these reactions, right. We will take another example and see what happens there. See, slowly we will start doing more examples. Okay. A system like this now. Okay, I have taken this. So, still I am not introduced any concept of like most of the time I have kept symmetry on both sides of your carbonyl. That itself first we will try to understand. If I bring some dissymmetry, then it will be really hard again. Okay. We will work with this example first, then we will take some better examples, like tougher examples. So, here you know that it goes, see why I am writing this S1 and T1, because you will be getting bored writing S1 and T1. See, some cases reaction gets stopped from S1 and does its chemistry from S1 itself. You should understand what are the cases where it stops S1. See, this intersystem crossing, if the, I said why S1 to T1 should happen if the energy gaps are very small. So, you should understand that depending upon your ketones, whether this ketone can undergo an intersystem crossing. Okay. So, that is why I am writing this again and again. Because this is only the photochemistry part. Now, we get a system like this. Okay. This is your primary. Now, we will see what chemistry is going to dominate in this. So, what chemistry we can think about here? Now, we have like 3 process, because we know it is a cyclopentanone system. So, is radical recombination is, can we think about radical recombination? Can you make a again a strain type of ring, because it has, okay, that is not possible. Then alpha cleavage, why alpha, why decarbonization should not take place here? I can decarbonylate this, okay. I can join, because that product is, you cannot have like 3 cyclobutane system, right. No. So, then you are avoiding that decarbonization step now. So, the only one you are left is intramolecular hydrogen abstraction, right. See, now I can generate 2 type of alkenes here. See, for example, I just for our convenience I am numbering this 1 3, like this I am numbering. Okay. This acyl radical can abstract an hydrogen from here, from 4 to give me a alkene, yes. But same way this acyl radical can also abstract an hydrogen from 6 to give me an alkene. So, it can get me 2 products now. Okay, it is not like it will end up, both the products are formed. Okay. Get an aldehyde, alkene,
that parent diuretical can undergo decarbonylation to give rise to a 1,4 diuretic.
Diuretic.
It can undergo beta cleavage.
Cleavage. But that never happens, that decarbonate. Immediately before that it undergoes an hydrogen abstraction to give me the aldehyde. That process is more faster than that. Okay, that is the only reason.
It can give rise to 1,4 diuretic.
1,4, yeah, that can cleave back to give me 2 cyclobutanes. Yeah, that can happen. But these products are more predominating that. If I say you can think about all the products, then that is the criteria. You can think about that, is nothing wrong in it. Okay. When you talk about more dominating products, okay, in a liquid phase, then this comes as a dominating product. Whatever you thought is completely right. Okay. Now you have a system of this. Okay. What you can expect. Yeah, as I anyhow, I am not getting bored with this. I will write down to give me my get this. Now, what chemistry can dominate here? What are the secondary process I can think about? Shall we write one product and see whether it can be formed? I can abstract an hydrogen, okay, from here to give me a ketene. And get a ketene. Okay. Or I can look for acyl radical abstracting an hydrogen. Is that is possible to give me an alkene, because you can get a nice alkene then. And get an aldehyde like this. See, it can undergo a bond rotation now, okay, and then it can recombine. See, in this case much of decarbonylation we are not seeing. See, it depends upon individual examples. Now, like once you know primary process, then you are getting into secondary process. In secondary process, you should understand depending upon the molecular structure, like how the given compound looks like, which product will be dominating, whether it is an decarbonylation or it is an intramolecular hydrogen abstraction or it is formation of my 1,4 diradical, which is dominating. See, when you go for specific example, one of the product will be major most of the time. Okay. Then you have to identify which is the major product. Clear? So, we will get lot of examples. See, that is why since I am doing cyclopentanone system, then for you it is looks like very easy. you can just draw the structure, because I am taking say 5 member ring. Once we do an example where I will include all the things together, that time we will see how we can do, how tougher it will be. Okay. Clear? Okay. We can have a break now, then we will start cyclobutane system.